welcome to lecture 20. So, for today we will lay the framework for a very important and useful paradigm for algorithm design, namely randomized incremental construction. This method actually goes way back, to 30-40 years ago, and perhaps can be thought of as one of the first formal algorithm design techniques, although it was not known to be in this not known under this name at that time. And subsequently, over the years, as people discovered more and more algorithms that kind of can fit this framework, it was formally christened as randomized incremental construction. So, the basic framework is, as I said, goes way back to quicksort algorithm actually. And if you think about the quicksort algorithm, one way to describe it would be that you have given n elements to sort, and the usual way to describe it is that you pick a splitter or pick a pivot element that partitions the set into two subsets, and then you recursively sort the two subsets, right. So, quicksort can be thought of as pick a pivot element at random and split the set S into two sets. So, let us call this pivot element X, two sets S less than X and S greater than or equal to X, and then sort them recursively using the same method. That is, again, within each of these sets you pick a pivot element and then continue. Okay. So, this gives rise to a kind of a recursion tree, which is the set S, then depending on X. So, the subsets S less than X and S greater than or equal to X, they depend really on the choice of this pivot element. And if you recall your early courses in algorithms, the efficiency of this algorithm really depends on how evenly this set is split. So, if so this is your recursion tree, and then subsequently again you sort S strictly less than X and X greater than or equal to X in the same method by choosing pivots in these two sets, and you continue till your sets becomes the individual subsets become very small, like maybe if you want you can go all the way till it become singleton elements, but in most implementations of quicksort they terminate once you have, let us say, something like less than 10 elements or so. And the success or the efficiency of the algorithm really depends on how evenly the pivot partitions the set. Okay. So, if S is these two sets, okay, the size of this and the size of these are closely matched, okay, then it implies something like an order n log n algorithm. Okay. Since we are not discussing quicksort per se, let me not go into why this is so, but once they are evenly split, you can consider that the depth of this recursion tree is not going to be more than log n, and each level of the tree you are doing about linear work. Okay. So, this is the classical definition version of quicksort, and in fact, the classical definition probably does not even require you to pick this element at random, but there is a fairly big difference in picking this X at random vis-a-vis picking so choice of X, okay, Your two possibilities, one is pick the first element of S, okay, in whatever order it is given, or like in this version we have said pick a random element. The difference between these two versions is that in textbooks you will find that this is the version that is being analyzed, and then you can actually come up with a pretty bad permutation, namely that if you have your initial sequence of elements sorted in a reverse order, then when you pick your pivot in using this method, that is pick the first element, then you are going to incur a huge cost. That is, your first element is going to produce two very unequal subsets, namely one of just unit size, the other one is of the rest of the elements n minus 1, and then you have to keep continuing this, because your n minus 1 elements, then again when you pick a pivot, again you have you pick the first elements that again creates very unbalanced partitions, and this way you can get something like an omega n square kind of a performance. Okay. So, in many descriptions of quicksort, you hear this statement that quicksort has n square worst case complexity, and what they are really saying is if you pick the first element as the pivot, then for certain permutations, for certain worst case permutations, you will run into this pathological situation where your sets are very unevenly split. Right. Now, as opposed to this, if I pick a random element, although it seems like a rather subtle change and very small change, it can make all the difference in the following way. Now, if you pick a random element, which is, let us say, use a random number generator and choose any of these elements with equal probability. Okay. So, all elements are picked, okay, so uniformly picked. Okay. So, uniformly at random. Okay. So, any of these n elements can get picked, and so even the first element can get picked, but then the first element gets picked only with probability 1 over n, because all indices or all elements are likely to be picked as the pivot element. They are all equiprobable, and that is what makes now the situation difficult to construct a bad permutation. Now, what is the bad permutation? The bad permutation will completely depend on the choice of the pivots, which is not known in advance. So, you will not be able to come up with this pathological worst case situation, that is take this permutation and then you can force the algorithm to partition it badly. Okay. It will really depend on the choice of the random element. Okay. And that is why the other characterization of quicksort performance, which says that the expected time, the expected running time of quicksort is order n log n, okay, where the expectation is over the choice of pivot elements. Okay. So, this is a more accurate statement, and in this version of quicksort, okay, it is very difficult, let us say, with to create a bad permutation. In fact, even if you keep the same permutation and run quicksort again, it may not behave the same way, because every time you run quicksort, your pivot elements are going to be chosen independently, and therefore, you can't even force quicksort to have, let us say, 2 consecutive worst case runs. Okay. So, that is nearly impossible. So, you can claim that this statement holds with probability almost 1. Okay. And that is very different from the case where you pick the first pivot element, first element as the pivot, in which case the expectation or the average case is over the permutations. Okay. So, this is the over random choice. Okay. So, this is over random choice, whereas if you pick the first element, So, in this version of the quicksort, which is actually the classical version that Hoare described, then the average running time is order n log n, where averaging is done over the n factorial permutations, okay, n factorial permutation, because initially the n elements, let us say all of them are distinct, the initial input can be permuted any of the ways, okay, and if all these permutations are equally likely, okay, that is a very strong, that is what the averaging is being done over. So, the averaging is done assuming that all these permutations are equally likely, and then that gives rise to this average running time is n log n. Okay. However, as I said that there is no guarantee that these permutations are equally likely, you can actually get a permutation on which the quicksort will perform n square comparisons. But this is the version, or this is basically the crux of the general framework of randomized incremental construction. Okay. So, what we are basically saying here is that if I fix the permutation, because there are n factorial permutation of n elements, right. So, if I fix the permutation, if we fix the permutation, right, it basically means the choices of, it implies that the choices of the pivot elements are fixed. Okay. And if we fix the choice of the pivot elements, then there is no variation in running time, because I know that this is the first element is the pivot. So, when I get the input, I know exactly how it is going to split. Next time I know the second element will be the pivot. So, it just behaves in a completely deterministic predictable manner. Okay. And once you fix the permutation, okay, then the running time, there is no variation, right. So, we can actually claim that the running time of quicksort, okay, given a permutation, let us say pi, okay, let us call that. So, let us denote that by T n, okay, let me call it sigma instead of pi. T n sigma is the running time of the input for a given permutation sigma. Right. So, this is fixed. As I said, once you fix the choice of the pivot elements, the sequence of choice of the pivot elements, T n sigma is fixed, right. There is no variation. Right. And what this average case running does is simply claims that this T bar, which is the average case average running time of quicksort for sorting n elements, this is nothing but simply the averaging of that, assuming all permutations are equally likely. Okay. So, I will sum up the running time over all permutations. Okay. So, sigma is one of the n factorial permutations, okay, and of course, the averaging is done over all permutations. So, I should divide by 1 over n factorial. Right. So, this is what is meant by the average case analysis of the classical quicksort algorithm. So, given a permutation sigma, T n sigma is fixed, I look at all possible, I assume that all permutations are equally likely. So, I sum up the running times, this is the weighted average, okay, and the weights are actually equal because all permutations are equally likely. Okay. Stated in another way, okay, I can generalize this approach to other problems in the following way. So, what we do is initially generate a permutation. So, generate random permutation. given set S of call it sigma. Okay. So, initially my objects are given as, let us say, x 1, x 2, x n, an arbitrary ordering, and once you apply sigma to that. So, once you apply sigma to that, so x 1 is mapped to something, maybe it is mapped to x 6, maybe x 2 is mapped to, sorry, it is the 6th position, that is what I am saying. So, x is mapped to the 6th position, okay, x 2 is mapped to the maybe the 10th position, and maybe x 3 is mapped to the 1st position, and so on and so forth. Okay. So, this is what is happening. So, this is my random permutation. Okay. So, I can refer to these elements. The first element of the random permutation is nothing but sigma inverse of 1. So, sigma inverse of 1 is basically x 3, sigma inverse of 6, the 6th position is equal to x 1, and so on and so forth. Okay. So, when I want the first object of the random permutation, I say sigma inverse of 1, etc. Okay. So, that is the random permutation we have generated, and now it is a very simple framework where what you do is you just add these or consider these elements in the order generated by the random permutation. Okay. So, for I equal to 1 to n 2, okay, add, or let us say consider the set of objects sigma inverse 1, sigma inverse 2, the first I objects of random permutation. Okay. Let us call it S sub I. Okay. Now, whatever function or whatever computation you are trying to do, you do it on this partial input, right. So, compute it could be data structure, it could be a function. Okay. So, I am just say that data structure oblique function on S sub I. Okay. So, and that is it. So, finally, report the final result corresponding to S sub n when you have considered all the objects. Okay. So, this is the general framework of RIC. See, so randomized incremental construction. Of course, it is happening, or it is in the context of a specific function or a specific data structure. Okay. So, if it is something like sorting, like quick sort. Okay. So, in this step, compute the data structure of the function. Basically, we maintain the sorted subset of these elements. Right. It may not be immediately clear why we are saying that even in quick sort we maintain the sorted subset of I elements. Actually, if you think about it, we have not sorted the first I elements, but the pivot elements themselves are sorted, right. So, the I pivot elements, they are actually sorted among themselves, and the remaining elements are yet to be sorted, right. So, just to make this thing. So, we have some initial elements, right. So, you have some initial elements x 1, x 2 to x n. Right. At a point that we have chosen the first I pivots, right. So, I can mark those elements. Okay. Suppose these are the elements that have been chosen so far as pivots. Okay. So, you are maintaining a sorted set among these pivots. Okay. So, maybe the sorted set is this is the smallest element, this is the second smallest, this is the third smallest, and this is the fourth smallest. Okay. So, you are actually maintaining a sorted subset corresponding to the pivots, and all the elements that appear between the pivots, they are not sorted. Right. So, if I unwind this, okay, and I pretend that my initial set, I will consider these elements in a sorted fashion. Okay. So, suppose these are the elements actually in the sorted fashion. After I picked the I pivots, okay, I can represent the same diagram in terms of, so maybe these are the 4 elements that have been chosen, okay, and therefore, what remains to be done to complete the sorting is, so these are not yet ordered, elements appearing between the pivots are not yet ordered, and that is basically what the recursive calls to. So, you call the sorting recursively on this interval, and so on and so forth, and therefore, finally, the sorted set is just pasted together. So, that is precisely what we mean by when you say that the partial computation corresponding to SI depends on the problem at hand. So, in quicksort, the partial ordering corresponds to the sorted ordering of the pivots, and the elements between the pivots are not yet totally ordered. Okay. The reason I am trying to explain everything in the context of quicksort is the geometric problems are probably more difficult to visualize in terms of what happens when you insert the objects randomly. This is a simple enough problem, so that I can take up and explain the framework and do an abstract analysis without getting into the details of the geometric properties. Okay. And finally, when you analyze this thing, just as I said before, okay, so T n sigma, let us say, corresponds to the running time of a specific permutation, and these permutations are being generated at random. So, all permutations are equally likely. So, generate the random permutation. So, sigma is a random permutation, which means that each of these n factorial permutations are equally likely. So, and we are taking the expectation, okay, essentially over the. So, now I can say expectation over the random permutation, right. So, we are actually permuting the given set of objects into a random permutation, and in fact, when you do that, we do not keep the permutation as such, okay, and I actually randomly permute, and then I pick the first element of the pivot. This behaves exactly identical to the situation where you give me a permutation, okay, and I pick any element at random to be the pivot. Okay. So, these two are kind of now become equivalent, right. In which case you, so these two situations where pick a pivot at random, okay. This now becomes the same, or the behavior becomes the same as pick at element at random of the given permutation, and pick the first element of the elements permuted randomly. Okay. So, they have become equivalent. In one case, we are not changing anything to the given permutation, but then again I am choosing the pivot at random, whereas in the second situation we pick the first element, but then before we pick the first element, we actually permute the elements at random. So, they become equivalent, and therefore, the distinction that I drew between the classical version of quicksort and the random picking of the pivot, they now become equivalent, and now everything basically becomes. So, I can capture everything by this analysis, that the expected running time, now the expectation is over the random permutation. Okay. So, T bar n is the expected running time of the algorithm for over the choice of the random permutation. So, if the permutation is fixed, the running time is fixed. Okay. Permutation is the same as 1 over n factorial sigma belongs to pi. So, pi is the set of all permutations, set of n factorial permutations. T and sigma. Right. So, this is what is going to capture the running time of the algorithm based on RIC. So, I will say RIC for short for randomized incremental construction. So, here is basically where all the power is, or where all the action happens, that some permutations like we discussed for quicksort are bad, okay, but then again some permutations are good, because if in those permutations where we end up picking more or less the middle element as a pivot, those permutations are good. Now, the question is, over all choices of permutations, are we really doing well, or are we actually not doing well? Which way are we going? And it turns out that because given the average case analysis of quicksort, most permutations actually happen to be good, okay, and therefore you get that n log n kind of expected behavior. Now, for a generic problem, okay, it would certainly depend on the specifics of the problem, the properties of the problem. But what is quite amazing is that this framework, in the context of geometric problems, for many problems, okay, it actually leads to very good performance, which are basically provably optimal. Okay. So, but let me still expose this analysis with respect to quicksort, because as I am saying, then I can stay away from proving certain geometric properties, which may just be a little distracting from the actual crux of the analysis. Okay. So, let me try to analyze quicksort in a way that can be generalized to other problems, okay, under this framework, randomized incremental construction. So, this can be viewed as another way of analyzing quicksort, but then this is a very general way that will extend to many of the geometric problems. So, for instance, I am just to mention a few examples. The geometric problems could be, let us say, examples. Okay. So, examples, and these are actually done in practice, okay. Convex hulls. Okay. What do? You basically maintain a data structure. Okay. So, maintain the convex hull. So, what is required? A data structure is required, or some kind of computation is required to maintain the convex hull of the first I points of the first I points. Of course, these I points are being picked from that random permutation. Okay. Then another classical example which has been used very successfully is compute the closest pair of points. Okay. So, closest pair of points, in the closest pair of points, basically find the closest pair from among the first I points. And one of the things that we always try to do is, when we go to the next step, namely when we consider the next point, the I plus first point, we update the data structure. Okay, that is where the efficiency lies, in the data structure. So, I did not say much about the data structure, but when we are computing the data structure function S of I, we are, what is implicit in here is that we are doing some updates from S I minus 1, okay, using information of S I minus 1. That is, namely, when we added the I minus 1 object, we computed something, some data structure or some function, and then we add the ith object, okay, we do not want to compute from scratch, we want to somehow update the structure, and so that update cost, okay, we try to keep it as low as possible, and that is what leads to the efficiency of this approach. Okay. So, certainly we are not computing from scratch, that is why we are incrementally adding and incrementally modifying or updating this data structure. So, in case of quick sort again, when we add the when we consider the next element, okay, so you have this situation where there are, let us say, 4 pivots. When you pick the 5th pivot, okay, let me color it by different elements. Suppose I pick this as a 5th pivot. So, the only thing that I have to update is that, see, these intervals are not getting modified, okay, these are not modified, but only this interval, the elements correspond to this interval, they have to be now refined into 2 partitions, right, one to the left of this element, one to the right of this element. So, this is the extent of the update, okay. The others are basically not affected, and that is what we want to exploit or take advantage of. But then when we try to analyze this, it could become quite laborious that, see, when I pick the next pivot, okay, which I am saying is the blue element, it could, of course, it is coming from a random permutation. Any of the unadded object could be the next pivot element. Now, how do we know where this object falls, and depending on where that object falls, we will have to work with the elements in that partition. Okay. So, if the partition is large, then the more elements need to be refined into the 2 partitions, and if the interval is small, then there are fewer elements that have to be repartitioned. And because all these elements are equally likely to be chosen as the next pivot, it appears that this kind of analysis, if we try to do it from first principles, it is going to be very, very difficult, okay, because the probability that an element, the next element will lie in a larger pivot is much more, because that contains more elements, and if you are choosing the next element at random from the unadded element, which is what basically the random permutation does, there is a higher chance that we will pick elements from a larger partition, and therefore, one is inclined to believe that the expected cost, which is basically the cost of partitioning all the elements in that interval, okay, is going to be quite large, because smaller intervals, there is a smaller probability that we will pick the pivot from there. Right. So, this could be this is actually somewhat misleading, this intuition is kind of misleading, because why did this larger permutation occur? The larger permutation, the larger interval occurred because in the past the elements that we added, they were not picked very uniformly, okay, and therefore, that led to some variations. Of course, because we are picking elements at random, there will be variation in intervals, but then if they are more or less equal, then the work done when we pick up the next pivot element, that's predictable. Okay. In fact, the best way that it can happen is if that all elements, so at the stage I am picking the ith pivot, okay. So, if all the sets are of equal size, namely everything has size about n over I. So, these are the pivot elements, okay, and suppose all these intervals have equal size, okay, then actually you can do a calculation like so the amount of work done when so work done for the ith pivot, okay, is basically the ith pivot is irrespective of where this falls into, okay, maybe it falls here, okay, we are dealing with exactly n over I elements, okay, and only these n over I elements have to be repartitioned, and the cost is linear in the number of elements, okay. So, that cost is simply n over I, okay, and as you keep adding more and more elements, you basically have to sum this. So, let me put some big O just to make sure that it takes care of small variations, okay. This from I equal to 1 to n is nothing but big O of 1 times 1 over I is equal to 1 to n, and that is the magical figure of n log n. Okay. So, one would be tempted to believe that this analysis is too simplistic, okay, but it looks nice, right. I mean it gives us what we are looking for, okay. So, somehow we need to find a way to rationalize this calculation, and that is precisely what is going to happen now. Right. So, of course, I can't assume. So, this when we added the ith element, all the intervals were more or less equal. Okay. So, that we cannot assume because it is a random process. Okay. So, we will have to somehow analyze this random process rigorously, right. And for doing that, we will introduce some random variables. Okay. So, let us say that so, we will use something called actually an indicator variable. Okay. So, Zij okay, is equal to 1 if xi. Now, x1, x2, x3, xn are the labels of the elements in the input permutation. Okay. So, just to be specific, we are using that labeling. It does not matter which labeling you use, some unique way of identifying some element. So, all we are saying is that if xi is involved in the ith partitioning step, this variable is equal to 1, is involved in the ith. Okay, sorry, not the ith. So, this is a j. I am sorry. If xi is involved in the jth partitioning step, okay, I have to keep them distinct, and 0 otherwise. All right. Let us go back to this example. Okay. So, suppose I call these x1, x2, x3, some number x10 maybe, okay, x11, maybe this is x50, x51, etc. Okay. Now, what I am saying is that in the ith pivot step, so this red element is the pivot of the ith step, this is the ith pivot, and therefore, all the elements in the interval where this pivot elements belongs to, namely the second interval here, all those elements are going to be repartitioned, right. So, x10, x11, these are the elements that have to be actually reallocated if you are using an array in the array, or if you are maintaining some other kind of space. So, all the work is basically happening there. Okay. x1, x2, x3 or x50, x51, they are completely unaffected, right. And therefore, there is no, we are not going to be paying to move those elements. So, whatever cost we are paying for the algorithm in the ith pivot step can be charged to the intervals that are actually getting affected by this pivot. Okay. And that is precisely what this variable, or it is called, in general called indicator variables, indicator 0 1 variable. Right. So, these elements, so add for the jth pivot, if xi is actually involved in the partitioning, then we are saying it is 1, otherwise it is 0. Now, if we charge it this way, then the total running time of the entire process, this random process that leads to the sorting. Okay. So, we can say that the cost is basically put on the element itself. So, if this element x10 is getting repartitioned, we are putting some cost on that element itself. So, I can actually analyze or look at the running time by only looking at the cost charged to each element. Okay. And each element, is likely to get involved in further partitions down the recursive calls. Okay. So, the total cost, total running time, is just another way of adding up things. Okay. So, over all elements, over all partitioning steps, right. So, let us first look at the partitioning step, j equal to 1 through n, I equal to 1 through n, and z I j. Okay. So, the inner sum, this corresponds to total cost of a partitioning step. Okay. This is for all the elements. Okay. Only some of the elements, this Zij will be 0, exactly those elements that falls in the interval where the partition element falls in, right, and the remaining it is 0. And then I sum it over all the partitioning steps. Okay. So, the outer sum takes care of all the partitioning. Now, I can rewrite this again. So, let us call this total running time as t. Okay. So, t can be also I can just interchange the sum actually. I can write it as j equal to I equal to 1 through n. I am just interchanging the sum z I j. Okay. So, now I am summing for each element the total cost over all partitions. Okay. So, for each element the total cost over all permutations. Okay. Now, these are all all partitioning steps, not partitions. Now, whether or not a certain z I j should be 0 or 1 really depends on the random permutation that we are talking about. Okay. So, once you fix the random permutation, everything is fixed. Okay. But I have to do this analysis in a way that I am able to look at the expected cost over all random permutations. So, I will take the expectation on both sides. So, then ease of t is nothing but E of this whole thing, the double summation. Now, I will claim that this is less than or equal to n times the expected cost of a single element. So, the expected cost, the worst case expectation for a single element, if I can analyze that and multiply that by n, that will be my total expected cost, right. So, this I can rewrite as over all the pivot steps. Okay. What is the cost of a single element accrued by the single element in the worst case. Okay. And if I, since there are n elements, if I multiply that by n, this will certainly upper bound the whole thing. Okay. And now, I use on top of this the fact that expectations sum up. Okay. So, the linearity of expectation, and that is really the key of the analysis of randomized incremental construction. Okay. So, expectation of, I mean, this is classical result, right, ease of x plus ease of phi, and the beauty of this is it does not depend on whether x and y are independent. Okay. Even for dependent variables this goes through, right. So, for any random variables x, y. Okay. Now, I am suddenly talking about random variables starting from indicator variables. So, I am just renaming them, I am using the same variables, I am just calling them indicator random variables, because these variables can be 0 or 1 depending on the specific random permutation that we have chosen. Okay. So, I am not using the specific subscript. Actually, for all of these things I should have probably written a subscript, right, because just before I use the expectation. So, for a given permutation sigma, z I j will be 0 or 1, but now I am looking at the expectation. So, I do not have to look at a fixed permutation, but it is the expectation for all permutation, and at that point essentially the z I j's become your random variables. So, these are indicator random variables. So, now I can expand this and write it as less than or equal to n times, using the linearity of expectation, it is j equal to 1 through n expectation of z I j. Right. Now, what is the expectation of z I j? Z I j is 0 or 1, right, depending on whether or not the ith element is affected in the jth step or not. Okay. And that is nothing but this quantity is nothing but the probability that x I participates in the jth partition. So, it is a 0 1 variable. So, the probability that something is 0 times 0 is 0. So, it is only the other term, that probability that Zij equal to 1 times the probability equal to 1 is exactly this one. Okay. So, the whole thing comes down to analyzing this quantity n times j equal to 1 through n. So, what is the probability that Xij, or again going back to that, Zij equal to 1. So, what is the probability that a certain random variable will be affected? So, this will give us a bound. Okay. And how do we even analyze this? Because we really do not know how the previous, it's completely dependent on the choices of the previous pivots. Okay. So, for this we use a beautiful technique, okay, called backward analysis, and you will understand why it is called backward analysis. So, for that we will view it this way. Okay. So, we want to eventually analyze this quantity. What is the probability that a certain element will participate in the jth pivot step? Okay. Now, you will use just nothing. So, we can only use the fact that these permutations are random, and therefore, all permutations are not just random, they are picked uniformly at random, and there is a certain symmetry property of these permutations. Okay. So, namely, if you fix the first, so I am talking the jth pivot. Okay. So, fix the first j pivot elements. So, if you fix the first j pivot elements, then I can only, so there is of course, these first j elements, let us call it S sub j, okay, and then there are the remaining elements. So, we have fixed the first j elements of a random permutation. Okay. So, it is no longer that random, and so you have only choices to of permuting the remaining n minus j elements at random. Okay. So, by fixing the first j elements, okay, I can still permute the remaining n minus j elements, okay, and but I have, this is for a fixed choice of j elements. Now, all elements, all permutations are equally likely. Okay. So, all the number of permutations, so the number of permutations with Sj fixed, okay, is basically what? The way that you can actually permute the j elements here times the number of ways that you can permute the n minus j elements here. Okay. So, we have not lost anything, but we are only just fixing the choice of the first j elements. Okay. So, we are going to do some kind of a conditional calculation. Okay. So, by fixing the first j elements, we will find out this probability. Okay. So, we will try to compute the probability that Zij equal to 1, given that we have fixed a set of the first j elements, okay, because the other elements are not really going to affect the probability, right, but I have fixed this. Okay, and then once I can do this conditional calculation, then we should try to uncondition that. Now, again within this j elements, within Sj, all permutations are equally likely, right, of j elements are equally likely, okay, which means that so any of the j elements can be the last element of the permutation, equally likely. Okay. So, any of the j elements can be the last element, which means that if you fix an element, so for a fixed element, let us say y in Sj, the probability that y is the last element of a random permutation of S j is 1 over j, right. Any of these elements can be the last element. Now, we make a very critical observation. So, when is the ith element going to get affected? The ith element is going to get affected only when one of the, so this red element is the ith pivot chosen. Okay. On all the elements in the interval that this one falls into are getting affected. And so, for a fixed element, so for a fixed element like this, when is it getting affected? It is getting affected in the ith step if one of its two bounding elements change. So, the interval that contains it, if the bounding element changes, then this element is going to get affected, right. If you look at x 2, the bounding elements are not getting affected. Okay, so to be formal, we can introduce an artificial bounding element as minus infinity and plus infinity here. Okay. So, unless the bounding elements of the interval is getting affected by the ith insertion, okay, that particular element will not participate in the partitioning process. Okay. And so, how many elements? So, for a fixed element, let us say x 11, or for any other fixed element, what is the probability that it gets affected? The probability it gets affected is that the two bounding elements, one of the two bounding elements is the ith pivot, right. So, probability that z I j equal to 1 is the probability that one of the two bounding elements of x I is the jth pivot. Okay. And what is the probability? So, okay, so for a specific element to be the jth pivot, it is 1 over j. For two elements to be the jth pivot, okay, so that is basically equal to 2 over j. So, this is the probability that the ith element will participate in the jth pivot. Okay. Now, notice that although this is conditional, the probability was conditioned on choice of S j. For some fixed S j, we did this calculation, but it only depends on j. Okay. So, the conditional and the unconditional cost is same. Okay. The unconditional cost is same. And that follows from the symmetry, because all choices of S j are equally likely. Okay. All choices are equally likely. Okay. And therefore, we just got what we wanted. Okay. So, it is 2 over j. Okay. So, for the jth step, it is 2 over j. So, you go back to this calculation that we claimed was too simplistic. Now, it is actually exactly the same thing. It is exactly the same thing now, right. So, the probability, probability z I j equal to 1 less than or equal to, let us say, equal to 2 over I, okay, and therefore, summation, okay, over all I. So, jth step. So, that is basically bounded by the harmonic, which is 2 log n. So, for a single element, it is 2 log n, and therefore, for all the n elements, when you multiply by n. So, here is what we did basically, n times this probability, and this probability we computed to be equal to 2 over j. So, the whole thing is less than n log n. Right. So, this is the randomized incremental construction analysis. And this kind of analysis goes through for many other problems like convex hulls and closest pair, except that you have to apply it in the context of this specific problem, and you do this So, you have to come up with these figures in the context of the problem. This is for quick sort, but then again all these calculations are quite close to each other. Okay. So, we just have to give some thought to how you are going to actually do this analysis, but eventually this is what comes out of it. Okay. So, we will continue with more applications in the next lecture.